All right, welcome everyone to the ComSoc video seminar. It's great that you made it despite those deadline problems that have been mentioned. We're looking forward to another nice session. We have two mathematical economists with us today to tell us about what they've been doing. Before I introduce the first speaker, let me, for those of you who are here for the first time, I think there might be a couple of people, explain how things work. So we have two talks. Each talk is meant to be for 20 minutes and we have 10 minutes for questions afterwards. In between we have a break and we'll try to really simulate the coffee break atmosphere with our random breakout rooms. And we'll explain that again when we get there. During the talks, we figured out a good way of doing this is that if you have a question already during the talk, which I think some of you will, you type it into the chat. And the right way of doing it is like this. So you type uppercase question followed by your question, then because there might be lots of other stuff in the chat at some point, then it makes it easier to find the actual question. And then if some speakers have the cognitive ability to actually notice these things while they're happening and react to them, and the rest of us, we go after the talk and we browse through it, and then they can answer those questions, those that they have an answer for, that they feel like answering. And then also if at the end, if somebody wants to ask a question through the microphone, it's also possible, and we'll figure that out when we get there. Okay, Hans, I think you can share your screen. Okay. So our first speaker today is Hans Peters, Professor Emeritus of Mathematical Economics at the University of Amsterdam. I actually had the pleasure of attending his retirement party just before the Corona thing hit us in January. Although he's just told us before that he's now actually teaching, so it's still in the middle of it. Today he will be speaking about probabilistic social choice, and you may know some of his work on bargaining, on strategy-proof social choice. You may know his game theory book, these kind of things. And if you're ready, Hans, then I think we can start. Please go ahead.
Yeah, okay, I hope you hear me. Thank you very much, Ule, for the very nice invitation. So I will be talking about probabilistic social choice on graphs. As Ule mentioned, I had a kind of farewell party. I didn't really leave, of course, but that was last January, and I presented the same paper there, so some of you might have heard it already. Okay, so what is it about? Let's just start from the famous theorem of Gilbert and Satterthwaite. So we have finitely many agents. We have finitely many alternatives. Those agents have preferences over the alternatives. Those preferences are linear orders. There's a social choice function. Given the preferences, the social choice function picks an alternative. And we might want the social choice function to be dictatorial, to be strategy-proof, which then means that no agent can strictly benefit from not reporting truthfully. And then the theorem of Gilbert and Satterthwaite says that if the social choice function has at least a range of at least 3 alternatives, then there's a dictator. Okay, so this is, I guess everyone is familiar with that. There are also well-known escape routes. This is often seen as an impossibility result. So we talk about escape routes. There are many, but 2 well-known are, first of all, the theorem holds for the universal domain. So if all preferences are allowed, but that's not always the case. That's not always realistic. And in many cases, or there are cases where you can restrict preferences, in particular, restrict preferences to single peak preferences. I will come back to this, of course. This goes back to Black already, and Moulin, 1980, important paper. I'll also come back to that. The other approach was also by Gilbert, 1977 already. Suppose we assume that the social choice function doesn't pick an alternative with probability 1, but picks a probability distribution. Then what can we get? And again, we get, well, what you want, a possibility or impossibility result. We get random dictatorship here. Okay, so what we did already quite a while ago with Eders Peter Storken, We combined the two approaches. So we have single peak preferences, we have probabilistic social choice. So what do you get? That's what we did, paper 2003. And what we do in the current paper, in the presentation, so that's joined with Souvik Roy and Soumyarov Sadoukan. That is, we again combine these. So we have probabilistic social choice, we have single peak preferences, but now we have an arbitrary graph structure on the alternatives. If you look at the regular single peak preferences, like the Moulin case, that's on the real line. So you can look at this as a one-dimensional, as a line graph, one-dimensional thing, and now we look at general graphs. Okay, there's a lot of related work, but I'm not going into this. One of this is involved certain Peters, but it's not H. Peters, but D. Peters. There are many related works, but in view of the time, I will not go into it. Okay, so let's go back to the setting of Moulin, and in fact, Black already. So there's a set of alternatives, x1 and 2xm, and they are ordered. Let's say on a line, so elements of the real line, x1 smaller equal to xm. There are n agents, and those agents have single peak preferences on the set of alternatives. But there's one alternative that they like best, and if you go away in either direction, left or right, then preference decreases. Now suppose we look at a social choice function. So given a profile of preferences that picks an alternative, and we want it to be strategy proof and unanimous, and now just for the presentation, we want it to be anonymous. Okay, how does this work? Well, we have these alternatives here, they're on a line, x1 and 2xm. And what we could start with is we take any coalition S, because of anonymity only the size of S matters. We put the agents of S on the left point, most left point, x1. We put the complement on the right point, xm, so n minus S. And that gives us a preference profile. Peaks here of the agents of an S are on x1, and the peaks of the other agents are on xm. And that gives a certain alternative. Let's just call that, F gives a certain alternative, let's just call that F of S. Again, because of anonymity, only the size of the coalition matters. So we get here, let's say this alternative, for instance. Now, what can we say about that if we know that F is strategy proof and unanimous? Well, this is the picture again. Of course, if everybody here is on the left endpoint, then by unanimity, I haven't given you the formal definition, but I guess you know what it means. This will also be the point assigned, the solution. If everybody is here, then it will be xm, and otherwise it will be some point here in between. If the number of people, of agents on the left endpoint, if that decreases, then fs moves to the right. That is by strategy proof. So imagine there's an agent here in S. That agent jumps from left to right. Then he should not be able to improve the outcome, which means the outcome can only go to the right. So that's strategy proofness. And basically, this is the setting of Moulin. So what you get here is that if you have this, then for these profiles, F is completely determined. So F assigns the median of the reported points, PI, and those points, FS, that you get here. And also the other way around is true. If you choose here points, FS, respecting unanimity and respecting this property here, then this always gives you a social choice function that is unanimous and strategy proof. Again, for the presentation here, I assume anonymity, but you can also do this for non-anonymous social choice functions. So that was the paper of Moulin, 1980. Now we go to the probabilistic version of the same thing. So that is the paper that we did in 2003. Difference is that now F assigns not a single point, but assigns a lottery over those points. And strategy proofness now means again that you cannot improve by not reporting a true preference. This means that if you deviate, then there's another lottery, but this lottery is not better for you. To be precise, probability shifts away from your peak. Technically, this means that the lottery that results is stochastically dominated by the lottery from truthful reporting. Again, the same situation here. Again, for the presentation here, I assume anonymity. So now in the same situation, let's say a number of agents S, a correlation S is here with their peaks. The other agents are there on the left, on the right-hand side with their peaks. And then you don't get a single point, but you get some probability distribution. Let's call this f of s. And here again, if agents would not be truthful, so if a member of correlation S would jump here to the right, then yeah, you get a different distribution, and that distribution should be worse for the agent who was in X1. And this means that probability shifts to the right. Okay, so again, for all these profiles to get those distributions, in turn, how is the rule determined if you know all these distributions? So just assume that these are the reported peaks, P1 up to Pn. Then we get a picture like this. So we just assume here that the peak of 1 is to the left of the peak of 2 and so on. So suppose now we get all these distributions. Suppose we look at a point A here, where there's no agent, so it's not turtle, but no agent reports A. Then what we do is we take the closed interval from X1 up to A, and then we look at the distribution F, total probability by F, put on this interval. And for all the agents who are on this closed interval, in this case, those are all the agents from 1 up to L-1. And then we look at the open interval. So we leave out A, and again, we look at all the agents now on the open interval. In this case, it's the same agents. They are the same agents, so you get the same distribution. You subtract this from this, and then you get the probability that's put on A. If there's an agent on the point, on the alternative, you do the same thing, basically. But now it's going to be a difference. So let's look at this point, PL. You look at the closed interval from X1 up to PL. You look at FL on this closed interval with their peaks. And you look at the probability on this closed interval. And then you look at the open interval from X1 up to PL, but not including PL. The L-1 agents here, you take a different distribution, you take the difference here, and that gives you the probability on PL. And so in this case, for every point here, you compute the probability, and that gives you the rule. So our result was that all strategy proof, well, anonymous, but similar for non-anonymous rules, and unanimous probabilistic rules, they are determined by such fixed distributions. So again, you determine those distributions by looking at border profiles. So one set of agents on the left-hand side, the other set of agents on the right-hand side, and look at all the border profiles, and they determine your end distribution. So this is for single peak preferences on the line. You could say it's one-dimensional. It's a line graph, if you want. As soon as you extend this to higher dimensions, then again, you get random dictatorship. So it's really very sensitive to that. So under the analogous condition, if you have a set which is in higher dimensions and greater than 1, you get random dictatorship. Okay, so this is the history. And now we get to the paper that I'm presenting now, the new paper. So now the alternatives, it's still the same thing. There are finitely many alternatives, but now they are the nodes of a connected graph. Interpretation of this, you can think of a network of roads. You have to locate a public facility. You could also think more generally, this graph represents preferences with respect to several criteria. Okay, I don't have time to spend more attention on this. So let's go to the results. So we have a general graph. Paths, everybody knows what a path is. So just you go from one point in the graph to another point in the graph with all distinct alternatives. And a spanning tree is a subgraph containing all the nodes, but such that you have unique paths. It's a tree, so you have unique paths between every pair of alternatives. What are the preferences? Still linear orderings, still single peak, but of course now we have to be more careful. What does single peakness mean? It means one of the alternatives, one of the nodes in the graph is your top, TR. And if you follow, okay, no, let's start again. There is a spanning tree, so you have there's a spanning tree. One of the nodes is your peak, and if you go from this peak along the path in a spanning tree to different alternatives, then preference can only decrease. That's what this is. So that is single peakness on a general graph. Probabilistic rule, you assign to every profile of single peak preferences probability distribution, still the same. Unanimous, if everybody has the same peak, then you assign probability 1 to that alternative, that's unanimity. And probabilistic rule, unanimity, strategy proofness. The same as before, if you report a different preference, then the resulting distribution is stochastically dominated by the truthful distribution. So it's usual strategy proofness. It's a strong version of strategy proofness using stochastic dominance. Okay, what we do in the paper is characterize all strategy proof and unanimous rules for connected graphs, any arbitrary connected graph. A leaf, you know what a leaf is, it's an important concept here. It's an alternative that has degree 1. Don't have to explain that, I guess. What we do is we consider two extreme subcases. Namely, one case is where the graph is a tree, and the other case is where the graph has no leaves. And the general case follows from the combination of these two cases. So first we look at trees. So this is an example here. We have a tree. And the important concept here is what we call a leaf assignment. This is similar to the one-dimensional case. In the one-dimensional case, you put a coalition of agents on the right endpoint and a coalition of agents on the left endpoint. Here you do the same thing, but you distribute the agents over the leaves. In this case, A, B, C, D. And for instance, we have 5 agents here, and they are distributed this way over the leaves. And for every such leaf assignment, we're going to have a probability distribution. Okay, this probability distribution, these distributions have to satisfy two conditions, which are closely related to unanimity. If all agents are at the same leaf, that leaf gets probability 1. And strategy proofness, and what does that mean? For instance, here, if an agent, say agent 2, would go from leaf C to leaf B, then along this path, the probability can only shift from C to B, but of the path, so here and here, there, nothing changes. And that is, of course, closely related to strategy proofness. I got a message here. Okay, see, I don't have much time left, so let's hurry up a little bit. Yeah, so for all these leaf assignments, we have a probability distribution. And yeah, these probability distributions, in a similar way as for the one-dimensional case, they determine, again, for arbitrary profile, they determine the distribution that we get. So for instance, suppose here we have the same example, our agents 1, 2, and 4, 5. They are on these two nodes, and agent 3 is on this node. And so, for instance, we have these probability distributions. And what is, for instance, the probability that is put on E? Then we look at the point E, and we take two arbitrary vertices here, leaves, A and C. And first, we take an assignment where all the agents on the closed interval from E to A are moved to the point A, and the other agents here, 4 and 5, are moved to the point C. And second, we look at the open interval, and then we move only 1 and 2 to A, and we move 3, 4, and 5, we move into C. So we get this is a leave assignment, this is a leave assignment. We get these 2 leave assignments. And now the probability that's put on the point E, we take the blue assignment here, and we look at the total probability that is associated with the corresponding distribution puts on the closed interval, closed part EA. And we look at the red one, and we look at the probability that this puts on the open interval EA, and we subtract one from the other, and then we get the probability on E. So that's how these things work. So it's similar to the one-dimensional case, but now, yeah, it's for these general leave assignments. And so the theorem for trees says that this way you get exactly all the unanimous and strategy proof social choice, probabilistic social choice rules. Yeah, let's skip that. That was one extreme case, trees. The other extreme case is a graph without any leaves. What we first do is we look at 2 connected graphs. So it's a graph without leaves, of course. And for every 2 points, we have a cycle containing these 2 points. What we show there, I don't have much time, so let's do this quickly. What we show there is basically that we have always random dictatorship. So every agent gets a fixed probability. And then, yeah, to every node, to every alternative, you assign the probability of the agents who are on this node. So it's what's called a random dictatorship. That's for 2 connected graphs. This is in fact not very difficult. It's in fact the easiest part of the paper to prove. In the next step, we take an arbitrary graph and also, but a leafless graph. And now you can decompose this into maximal 2 connected subgraphs, like this, for instance, here. This is called a block tree. I looked it up. This goes back 100 years ago or so. It's very old stuff. But you can always do this. And so what we show next is that if you have a unanimous and strategy proof probabilistic rule and you have a situation like this, then of course, by the previous result, you get random dictatorship here, and you get one there, and you get one there. But what we show is that, in fact, all those random dictatorship are the same. They have the same weights, and they spread out over the whole graph. So in fact, we have random dictatorship. Okay, that's a theorem for leafless graph. And then the final step, we combine these 2 things. Now we have an arbitrary connected graph. And you can always split it up as follows. You take the subgraph in the red ellipse. This is the maximal leafless subgraph. And if you do that, then what's left are those things here, in this case in the blue circles, and those are the branches of the graph. And so what we know is we have random dictatorship here, and we have something else there, and we have something else there. And that's exactly what we get, but there are connections between these weights of the random dictatorship and between these things. So what we do is we take this graph, we take an arbitrary spanning tree. So in this case, yeah, we just leave out the 2 black things and we have a spanning tree. It's arbitrary as long as it's a spanning tree. We have random dictatorship weights, and we have a collection of leave assignments, so both these ingredients. But on these 2 things are connected, so we have additional conditions. And the conditions are that if you look at the leave assignments, for instance, you have this part here, for the agents that are on this leaf or this leaf, again, you get weights, but the total probability that's put on this part is the sum of the random dictatorship weights of the agents who are put there. The same is there. So that's the connection between these weights, random dictatorship weights and the leave assignments. Yeah. Inside, so the maximal leafless subgraph here, you just going to get random dictatorship. So if you have agents on this leaf or on this leaf, then they just get the probability assigned here will just be the random dictatorship weight of those agents here. Okay, and that's a general theorem. If you do this, you have an arbitrary connected graph. You fix an arbitrary spanning tree. So the rules are not going to depend on how you choose a spanning tree. And then phi is unanimous and strategy proof, even only if you have these random dictatorship weights, you have these leaf assignments, and they have these connections just formulated. Yeah, that gives you exactly all the rules that are unanimous and strategy proof. Okay, I guess my time is up. I'm looking at Ulle. He would probably not, yes, so my time is up. So I'll skip the example here and the concluding remarks. And thank you very much for your attention.
Thank you very much. Let's have a round of applause. Unmute yourself for Hans. And then I hope that people have been thinking about some questions. So nobody has typed in anything, I think. No. So I'll give you a moment to think. If you want to, you can also unmute yourself and ask. That's also fine. Close that.
I'll ask a question. This is John Waymark.
Yes.
Do you know Alex Refkin's JET paper? This was deterministic from about 5 years ago. And
yes, I know that paper, yeah.
Yeah, because he was looking at a class of what he called multi-dimension single peak preferences. And so you had some pre-specified, you look at different pre-specified orderings of the alternatives, and if people's preferences were single peaked over all of them, that identified a subset. But basically, the strategy proof rules he got have a flavor similar to what you've done, in that there's a region where it's kind of the standard results, but then outside that region is dictatorial. And I just wondered if there's some connection between what he did and you're doing, if there's some way of thinking of working on your graphs as looking at stuff generated by multiple single peaked orders.
Yeah, John, thank you for the question. So that's, I indeed didn't think of the paper by Alexander Refkin. So, but that is also closely related to a paper which is about, yeah, also something like in the beginning of the century, paper by Schumann and Vora. And that is also on graphs. And in fact, it's deterministic, so that's of course an important difference. And what they find is a similar thing. They find if you have trees, you have this kind of median kind of rules. So you have a possibility result if you want. If you have no leaves at all, then you get random dictatorship. So that result is in spirit for the deterministic case, not random dictatorship, it's dictatorship, so it's deterministic. So in that sense, that result is similar. Logically, you cannot really compare it, because in their case, when they talk about a graph, then every alternative, so look at this graph as a subset of the plane geometrically, and every point of the graph in their case is an alternative. So they have infinitely many alternatives. Their preferences are single peaked, and they just measure Euclidean distance along the graph. But yeah, so logically, you cannot directly compare the two approaches for the deterministic case it is. But in spirit, those results are the same. And I have to look again at this paper by Alexander Refkin. But I guess that will again be the same spirit. There's even an older paper by Danilov, which is only on trees. And again, he finds similar results as we do, but I think his class of preferences is higher than that. So yeah, those papers, all the basic models are not directly comparable because they're all a bit different, but the spirit of result is very much the same. Yeah, that's right.
Okay, Markus, do you want to unmute yourself and ask your question?
Yeah, thanks. Nice talk, Hans. Just to make sure I understood the single peaked preference definition. So if I remember correctly, you were saying that you just need existence of one spanning tree, such that if an alternative is between the top and some other alternative, then the middle alternative is preferred to the other alternative. So does this imply that if you have like a cycle, then you have lots of indifferences between? So let me ask differently: is it necessarily the case if two alternatives are part of a cycle that you have to be indifferent among them?
No, you can take, so how do you choose one preference? You just pick your spanning tree. And that spanning tree determines your preference.
Oh, I see.
You
So
can also pick a different spanning tree and then you get a different preference. So it's not that you pick one spanning tree and all the preferences are single peak with respect to one and the same spanning tree. But you can pick different spanning trees. So yeah, in general, this means that that you can be there are parts of the graph that you can order differently. If you're not on a path from the peak to that point, then yeah, it can be higher at some other points or lower in preference at some other points. But so you start by picking a spanning tree, and given the spanning tree, you pick a point, and that determines your preference. Not completely, but it determines your preference, part of your preference. Yeah.
Thanks.
Okay.
Okay, then there's a question by Harris in the chat. You can read it, or if Harris is fast, he can unmute himself and ask in person.
Yeah, have you considered weak strategy does not lead to? Yeah, that's a good question. The answer is no. I mean, we haven't considered that. It's true that strategy proofness is very strong because it requires not only that you cannot do better, but it requires actually that you do worse, or at least it requires that you can compare the two lotteries that result. And of course, you could just say that, if you're not truthful, then you get a lottery that you cannot compare to the original. That could be possible as well. So that's a weaker version of strategy proofness. And no, it's a good point, but we haven't looked at that. So I don't know what would happen in that case. I guess you get more rules. That's of course, but that's an obvious thing.
Okay, are there more questions?
Yeah, let's see.
There was an answer to a question.
Intuitively for cycle, can you cut it to get the line and then be single peak on the line? Yeah, I guess the answer is yes. That's similar to Marcus' question, I suppose.
I think it was an answer to or a comment on Marcus's question.
Oh,
yeah.
Okay.
Yes.
Oh, yeah, okay. That was so.
Concurrently with your own
I
answer.
agree.
Yeah.
Okay.
The other Peters.
Can I ask something?
Yes, please do.
This concept of single peakness, assume that you have some metric on the nodes of the graph. So you have a distance notion. Can you then take a concept of single peak that there is one node in the graph which is most preferred, and that if the distance in the graph becomes larger than the preference, decreases regardless how you traverse the graph? Is that a possible interpretation? So for example, if the graph is a grid-like structure, if you move away from your most preferred situation, the distance increases. As long as you only take upward or leftward steps in the same direction.
Yeah, there is a way. So what we do, there is a way, but I would have to think longer about it. You can express it in a somewhat different way. I don't know if that is what you suggest. What you say sounds like what I said about the paper of Schumann and Vogel, but there's very simple because the graph is seen as a part of the plane, and then you just take Euclidean metric. And so you travel along the graph according to the Euclidean metric, and that determines exactly the distance and determines exactly your preference.
You could do that in principle on any graph if you have some metric on the nodes.
Yeah.
Doesn't have to be Euclidean, for example.
Yeah. Well, I don't think you can really do that, because you see, as long as you follow from the peak, as you follow a path, preference decreases. If you follow a different path in a different direction, preference also decreases. But our assumption says nothing about how you compare the alternatives on these different paths. So in fact, you could alternate them. Right? So you go from the peak to the left, say, that becomes worse. You can go to the right, that becomes worse. But this left and this right endpoints, you cannot say anything about that. One could be preferred to the other or not. So
okay.
I'm not sure if you can then represent this by a metric, but
we have to move on. Let's take the one final question that you can find in the chat at the bottom by Alina. Maybe you can answer that, and then we're gonna have to break.
Is there a simpler way to present the result if you're only interested in deterministic mechanisms? Well, yeah, let's put it this way. I don't know if that's a simpler way, but if you're only interested in deterministic mechanisms, basically what you do is that, so instead of random dictatorship, case where you have random dictatorship, you get dictatorship. That's of course clear. But otherwise, yeah, what you do is you just look on a path from one leaf to the other leaf in the graph. And basically what you do there is you can express the alternative that you get in terms of medians, like in the case of Moulin. That's actually how, if I remember well, how Schumer and Vora do it. They don't look at what we do, these leaf assignments, but they look on assignments for every possible path, from one end leaf to the other end leaf, and they work with these things. Now, I'm not sure if that is simpler, but of course, if you just have deterministic mechanisms, everything looks a little bit simpler.
All right, thank you very much. That was nice. Then we are going to have our break now. So again, for people who haven't seen this before, in a moment, you're going to see on your screen an invitation to enter breakout room number N. And then if you press yes, there will be some flickering on the screen. And after a few seconds, you'll be taken to another thing like this. And in expectation, you will meet around 5 randomly selected people that are currently here. And you can have a chat with them. And then you come back in 10 minutes. You'll get a message. Now you have to come back, and then we meet here again for the next talk. So I see you all in around 10 minutes time. All right, Marcus, you want to share your screen while I introduce you? So I hope you all had a wonderful break. I certainly did. Our next speaker is Marcus Pivato, professor of economics at Cergy near Paris. He's been working within social choice. He's also done other things, for example, on judgment aggregation, epistemic social choice, some work on deliberation. Also, he's been organizing, from what I hear, it was a nice workshop, couple of editions of that workshop that I missed on deliberation and that kind of things recently near Paris. I remember the first time I don't think met, but I've seen a talk by him was in Social Choice in Welfare at the Congress in 2010, in the hot summer of 2010 in Moscow, where he somehow managed to get 2 slots next to each other, which is not supposed to be allowed. And he was like running through. It was a little bit intimidating, but ultimately satisfying. And maybe it's going to be a little bit like this today as well. We'll find out. So Marcus, the floor is yours.
Thank you very much. So just to be clear, in 2010, my co-author canceled. That was what happened. So it's not that I bribed somebody, but yes. Okay, so thank you all very much for being here, and thank you very much to the organizers for inviting me. So I'm going to be talking about Bayesian social aggregation. So let me just start by sort of telling you what social aggregation is about, or Bayesian social aggregation. So let's start by looking at sort of two of the kind of central questions of normative economics. So first of all, there's the question of individual decision making. So the question is, how should an individual, how should a rational agent make decisions when faced with risk or uncertainty? And the other big question in normative economics has to do with group decision making. And so now the question is, how should the individual utilities be aggregated together into a social welfare function? Okay, so in 1947, von Neumann and Morgenstern famously came up with an answer to the first question, and they looked at an individual and they said, if this individual satisfies a few simple and compelling axioms of rationality, then this individual must make decisions as if she is maximizing expected utility. And in 1955, Harsanyi used the von Neumann-Morgenstern framework to develop a solution to the second question. And so what Harsanyi showed is the following. If all of the individuals are von Neumann-Morgenstern expected utility maximizers, and the society or the social planner is also a von Neumann-Morgenstern expected utility maximizer, and satisfies the ex ante Pareto axiom with respect to the preferences of the individuals, then the social welfare function must be a weighted sum of the utility functions of the individuals. So the kind of slogan here is that von Neumann-Morgenstern rationality plus the Pareto axiom implies utilitarianism. And Harsanyi regarded this as a very strong argument in favor of a sort of a fairly bold claim in moral philosophy, which is that social decisions should be made using a utilitarian method. But there's a problem with this, and the problem is that the von Neumann-Morgenstern framework assumes that all risks can be described using sort of objective probabilities which are somehow scientifically determined and they're known by everybody. And in some situations that's realistic, but in some situations that doesn't seem very plausible. So for example, if I ask you, what is the chance of a stock market crash in the year 2035? We might have opinions about that, but it's difficult to kind of assign an objective probability to that event. Right? So there are many situations where there's no way to assign these kinds of probabilities, at least objectively. And so around the same time as Harsanyi, Savage was developing a different approach to decision theory, which allowed us to deal with these kinds of situations. So in the Savage model, there's a set S of possible states of nature, and the true state is unknown to us. And there's a space X of possible outcomes. These are the things that we care about. These are the things that are going to give us utility. And in the Savage model, an act is a function mapping states into outcomes. So acts represent, courses of action or policies that you could take as a decision maker. And Savage assumed that the agent has preferences over these acts, and he showed that if these preferences satisfy 6 axioms of rationality, then there is a unique probability distribution P on the space of states of the world, and a utility function U on the set of outcomes, such that the agent's preferences over acts are described as if the agent wants to maximize the P expected value of U. And so this is called subjective expected utility maximization. And the reason is that the probability P represents the agent's subjective belief. So this is not a description of some objective fact in the world. This is just a description of something which happens inside of the agent's mind. And the important point here is that different agents might form different subjective beliefs, and there's no criteria by which you can say that some subjective beliefs are better than others. So now we can form a nice sort of 2-by-2 grid where we compare individual and collective decisions, and we consider objective probabilities versus subjective probabilities. So if we're looking at individual decision making with objective probabilities, then we have the von Neumann-Morgenstern expected utility maximizer model. And if we're looking at collective decisions with objective probabilities, then we have the Harsanyi social aggregation theorem for utilitarianism. And if we're looking at individual decisions with subjective probabilities, then we have Savage's subjective expected utility model. And so, of course, this raises the question, what goes in the fourth corner of the box, right? What is the correct way of thinking about collective decisions with subjective probabilities? Or to put it another way, is there something like the Harsanyi social aggregation theorem in a situation of subjective uncertainty in the Savage model? So in 1995, Philippe Mangin showed that the answer, in fact, is no. Okay, in the Savage framework, the Harsanyi theorem is false unless all agents have the same subjective beliefs. And in fact, he showed that if the agents have different subjective beliefs, then it is impossible to satisfy the ex ante Pareto axiom. Now, of course, in general, there's no reason why agents should have the same subjective beliefs, because as I said, these things are just sort of a product of their subjective psychology. And so this theorem is generally interpreted as an impossibility theorem. And so that's basically where things stood for about the next 10 years, until a very important paper by Gilboa, Samet, and Schmeidler in 2004. And so what they basically said is they said, well, there are going to be certain events for which all agents assign the same probability for whatever reason. And let's look only at acts which depend upon these events whose probabilities the agents agree on. So we only care about acts which are measurable with respect to the acts where all the agents agree about their probabilities. And we're going to only apply ex ante Pareto to comparisons between those kinds of acts, okay? And they showed that the social planner satisfies this restricted ex ante Pareto axiom if and only if two things are true. First of all, the social welfare function is a weighted sum of the individual utility functions. And second of all, the social beliefs are a weighted average of the individual beliefs, the individual probability distributions. Okay, so the slogan basically is that the Gilboa, Samet, Schmeidler restricted Pareto axiom implies both that the social welfare function is utilitarian and that the social beliefs are obtained through a linear pooling of individual beliefs. So this is a very important and powerful result. It's a landmark result, but it has some shortcomings. And the first shortcoming is that the linear pooling rule does not really respond very well to the arrival of new information, right? So if new information arrives, we expect that the individuals are going to update their beliefs using Bayes' rule. And we would also expect the social planner to update her beliefs using Bayes' rule. But the problem is that these two processes are not going to agree. So basically, sort of roughly speaking, the Bayesian update of the weighted average of the individual beliefs is generally not going to be the same as the weighted average of the Bayesian update of the individual beliefs. So these two operations do not commute. Okay, so linear pooling is not compatible with Bayesian updating, basically. And in fact, the Gilboa, Samet, Schmeidler Pareto axiom also does not respond well to the arrival of new information. You can construct examples where you have a bunch of agents who satisfy there's examples which satisfy the Gilboa, Samet, Schmeidler Pareto axiom. But basically the reason is because different agents start with the same beliefs, they update on different private information, and then they kind of accidentally agree about the probabilities of certain events. So they agree about certain probabilities, but the agreement is kind of accidental, okay? And that can lead to sort of absurd consequences. So basically the upshot is that there are situations where the Gilboa, Samet, Schmeidler Pareto axiom and linear pooling are not appropriate, in particular situations where we see the arrival of new information. And this suggests that the social welfare function and social beliefs maybe should not be obtained using the same rule. Maybe they should be obtained independently using different methods, different axioms. And indeed, there might be some situations where the social beliefs should not be obtained by aggregating individual beliefs at all. Okay. So that's kind of the historical background. So now I'll tell you about the model that I want to present. Okay, so my model is going to be based on stochastic processes. So I need to sort of briefly review some ideas about stochastic processes. So throughout this talk, n denotes the set of natural numbers, including 0. S is a finite set. And S to the power n is the set of all n indexed sequences of elements from S. I'm going to write such a sequence as a bold-faced S, and its entries are S sub t. So the way you interpret this is that the elements of S represent sort of individual states. They represent instantaneous states of some process. And the elements of S to the power n represent histories of that process. This is a process which is unfolding over time. So you can interpret a history as a flow of information which is revealed over time. And S sub t is the information which is revealed at time t. Okay, so here are some pieces of notation which I'll be using later. So for any capital T, any natural number capital T, S0 dot dot capital T is just the sort of finite segment consisting of the first T elements of the history. So you can think of this as all of the information that is revealed up to and including time T. And meanwhile, ST dot dot infinity is the set of, is sort of infinite sequence of all states starting at time T. So this is all the information that will be revealed after time T. Okay, so now what is a stochastic process? A stochastic process is just a probability measure on the space of all possible histories. And I'm going to represent that using the letter rho. Okay, and so the key idea in the model is the true state of the world is some unknown element of the space of histories, right? The true future history of the world is unknown to us. every agent's beliefs are described by a probability measure on the space of possible histories. In other words, every agent's beliefs are a stochastic process. And as time passes, the agents observe information, they learn about the true history, and they update their beliefs accordingly, okay? So that's basically the way the model is going to work. All right, to keep things simple, I'm going to be focusing mainly on Markov processes. This is sort of a simple class of stochastic processes. Most of you know what a Markov process is, so I'll just review it quickly. So if I have a non-negative vector indexed by S, I'm going to say that it's a probability vector if its coordinates add up to 1. And a stochastic matrix is an S cross S vector of non-negative real numbers, such that every row vector of that matrix is a probability vector. Okay, and so basically, if I have a stochastic matrix, P, and I have a probability vector Q, then I can put them together to get a Markov process defined in the following way. So basically, the idea is I use Q to decide what is the probability distribution over the initial state of the process, and I use P to decide what are the probabilities of transitions from one state to the next, okay? So basically, given any initial segment R0, R1 up to RT, some initial sort of instantaneous states, the probability that the history starts with R0, R1 up to RT is given by, first of all, Q of R0 is a probability starting in state R0, times the probability of transitioning from R0 to R1, times the probability of transitioning from R1 to R2, etc., times the probability of transitioning from RT minus 1 to RT. So this is a very natural way to build a stochastic process. One more piece of terminology. I'm going to say that this process is non-atomic if there is some natural number n such that all entries of the matrix P to the power n are strictly less than 1. Okay, so intuitively what this is saying is that there is no periodic trajectory that occurs with positive probability. All right. Now let's basically talk about how agents have preferences in this model. So as I said, the set of states of nature are these histories. So we're going to introduce a space X of, and the true history is unknown. We're going to introduce a space X of consequences. And now an act is going to be a measurable function alpha that maps every history into some consequence in X, okay? So let A be the set of all acts. Let I be a set of individuals, let O be a social planner, and let J be the union of I and O. So J is the set of all agents in the model, okay? So for every agent little j, I'm going to use this notation here to represent J's preference order over acts. And as usual, these preference orders are assumed to be complete, transitive, reflexive binary relations. Every agent J has a utility function, U sub J, which assigns a real valued utility to every outcome. And so let rho J denote the beliefs of agent J. Okay, so this is a stochastic process. It's a probability distribution over the space of histories. So the first assumption in the model is that every agent is a subjective expected utility maximizer. What that means is given any acts alpha and beta, agent J prefers alpha to beta if and only if the expected utility of alpha is greater than or equal to the expected utility of beta according to her beliefs and her utility function. Secondly, for simplicity, I'm going to assume that the beliefs of all agents are Markov processes. Okay, so I want to emphasize this is not essential. This is just for simplicity in the presentation. And the third assumption is that the beliefs of all the agents are concordant. So what that means is that there is some non-atomic Markov process mu, okay, which is absolutely continuous with respect to the beliefs of all of the agents. So what that means is for any event B, any subset of histories, if some agent assigns that event probability 0, then mu must also assign that event probability 0, okay? So this is basically a kind of a weak consistency condition between the beliefs of the different agents. Basically what it's saying is that the supports of the different agents' beliefs cannot be disjoint from one another, okay? Now it's important that mu itself does not necessarily represent anybody's beliefs. And also, I don't require the beliefs of the agents to be non-atomic, and I don't require the agents' beliefs to be absolutely continuous with respect to each other. All right, so that's what's happening in the background. So now I need to introduce conditional probabilities and conditional beliefs. So for any time t and any initial segment q, from time 0 up to time t, I'm going to use rho jq to denote agent J's conditional probability over the future given an initial history Q, given the initial segment Q. Okay, so how is that defined technically? Well, given some subset B over the space of all future histories, so basically history starting at time t up to infinity, the conditional probability of B is given by this formula here. I'm not going to read this formula, but basically the idea is something like this. If we imagine S is a random history drawn from the probability distribution rho j, then rho jq of B is basically the conditional probability that J assigns to the event that the future of the history S lies in B, given that the history so far matches the initial conditions Q. Okay? And then given some history S and some time T, I'm going to use the notation rho JST to denote the conditional probability generated by the first T elements of Q. Of S rather, okay? So basically the idea is this is agent J's conditional probability over the future, given that the history matches S for the first T period. So she's seen the first T periods of history S, and now she forms beliefs over the future based on that data. Okay, so this is just the sort of natural way that agents would form beliefs as they observe the process unfolding. Now, given their conditional probabilities, we can now give them conditional preferences, okay? So the stochastic process is unfolding over time. At time t, the agents have observed the first t values of the process, and based on this information, they can update their beliefs, like I showed you on the previous slide, and thus they update their preferences over acts. Now, an important point is that when the agents contemplate acts at time t, they imagine executing these acts at time t plus 1. So in other words, they do not imagine going back in time and executing the acts at time 0, because time 0 is gone. They always imagine executing the acts starting at time t plus 1. So what does that mean exactly? Well, there's a natural isomorphism between s to the power n and s to the power t dot dot infinity. It's the obvious thing. You just take every history and you shift it forwards in time by t plus 1 units. And that means that any act alpha mapping s to the power n into x can be transformed into a function, which I'm going to call t alpha, which just basically maps future histories into x. So basically, you can think of t alpha as it represents executing the act alpha at time t plus 1. So with that out of the way, we can now define preference orders, conditional preference orders as follows. So given any history S and any time t, we're going to define a preference order, which I'm going to indicate by this symbol on A. Okay, basically given any acts alpha and beta, this says agent J conditionally prefers alpha to beta, conditional on having observed the first t values of S, okay, if the expected utility of the time-shifted version of alpha is greater than the expected utility of the time-shifted version of beta, given her conditional beliefs at time t. So this is agent J's preferences over acts starting at time t plus 1, given that she has observed the history S up to time t and updated her beliefs accordingly. Okay, so this is the sort of rational way for agents to update their preferences as they acquire information. All right. So now I can define what I call eventual preferences. So let H be some event, some measurable subset of histories, and suppose that agent J assigns that event positive probability. So we can define a partial order, which I'm going to represent using this symbol on the space of all acts as follows. Given any acts alpha and beta, agent J eventually prefers alpha over beta on H if, for every history in H, there is some time t such that the agent J prefers alpha to beta conditional on having observed the first little t values of S for all little t greater than big T. Okay, so in words, what this is basically saying is if agent J observes any history in H for long enough, then she will eventually develop a preference for alpha over beta, which will then persist from that moment onwards. Okay. So let's use this symbol to denote the preferences of the social planner, the social preference order. So I'm going to require one axiom, exactly one, and here it is. It's the eventual Pareto axiom. So what this says is for any event H such that all agents assign that event positive probability, okay, and for any acts alpha and beta, if every individual eventually prefers alpha to beta on H, then the social planner must also eventually prefer alpha to beta on H. So in words, this is saying, if all individuals eventually prefer alpha to beta after observing any history in H for long enough, then the social planner should also eventually prefer alpha to beta after observing any history in H for long enough. All right, and now finally, we get to the main result. So here it is. So suppose that all individuals in the social planner are subjective expected utility maximizers. The social planner's utility function is the social welfare function W. And the utility functions of the individuals are here. And suppose that their beliefs are given by a concordant collection of Markov processes. Then the social preference satisfies eventual Pareto if and only if the social welfare function is a weighted average of the individual utility functions. Okay, I just want to make one remark. I've stated the theorem for Markov processes, but in fact, the theorem holds for any collection of stochastic processes. It's just the definition of concordant becomes more complicated. Okay, I'm just about done. Let me just sort of summarize what the theorem is telling us. So basically what I've done here is I've restricted Pareto to preference agreements that persist in some sense in the long run. And this restricted Pareto axiom implies that the social welfare function is utilitarian, but it does not impose any relationship between social beliefs and individual beliefs. And so therefore it is not vulnerable to the objections raised earlier against the linear pooling rule. So thank you very much for your attention.
Thank you very much. Round of applause, everyone.
Thank you. And
All
I would
right.
just like to say one more thing, which is that I would like to dedicate this to Philippe Mangin, who unfortunately passed away this summer. So.
Thank you. Okay, so we have already a couple of questions in the chat. You can maybe go to those and the two last entries. Yeah.
Oh yeah, that's a huge chat. Okay, let me, I guess, stop sharing my screen at this point is probably wise. Yeah. All right, stop share. There we go. Okay. From Peter, Markov chains have no memory, but your framework considers the entire history over the initial segments. Well, okay, so the general version, as I said at the end, involves stochastic processes, so it does not require, it is not just for Markov chains. I guess the way you should sort of think about it is that in general, an agent's beliefs can be thought of as a sort of superposition of many stochastic processes, a kind of a linear combination, because the agent kind of doesn't know which is the true stochastic process, right? And as they acquire more information, agents kind of learn, they're sort of engaging in a process of sort of hypothesis testing, and they kind of will assign more probability to some of these Markov processes than others, or more of some of these stochastic processes than others. So they'll sort of converge on knowledge of the true stochastic process. That's intuitively speaking what's going on in the model. So in that sense, even though the Markov process doesn't have memory, the agents do have memory. They're using their knowledge of what's happened so far to predict what's going to happen in the future. I hope that that answers the question.
The point was whether if you make the simplification that the beliefs are dependent on the states only, how much will that simplify your framework?
Oh, I see. The question is whether the agents update only based on the present. Okay, it wouldn't work at all. It's very important for that the agents use complete information of everything which has happened so far to update their beliefs. Otherwise, it's not going to work. I think does that answer the question? Okay. All right. Next, we have a question from Harris. Oh no, sorry, that's from the previous talk.
At the very bottom from Franz.
From Franz. Can you think of your act as something you do one time and whose consequences depend on a whole history of natural events, or as a plan or sequence of moves, in which case each move can respond to what happened and has been observed up until then? Okay, that's a great question. If I understand this question properly, it's more or less the same question which comes up when we compare normal form representations of extensive form games, right? So you can always take any extensive form game and look at a normal form representation where every sort of plan can be sort of collapsed into a single kind of, abstract strategy in the normal form. And that seems kind of counterintuitive because people think, well, a strategy in a normal form game is something that you sort of like execute, you commit yourself to it, and then you lose the ability to kind of react to circumstances later on. But that's kind of not the right way to think about it, because really a strategy in a normal form game is more like a complete description of how you would react to every possible contingency which will unfold in the future. Okay, so the acts in this model, the functions alpha, they map an entire history into a consequence. And so what that means is that each act implicitly encodes a complete plan for how you would react to every possible contingency in the future. So the act could be something which just kind of like determines a consequence based upon what happens today, but it could also be arbitrarily fine-grained description of future possible histories, and so it can encode any possible pattern of reactions you want. I maybe should mention that in the talk, to keep things simple, I just said let A be the space of all acts. Okay, in fact, you don't need all acts to get the theorem to work. You only need to look at acts which take only finitely many values. Okay, so in some sense, it's a smaller set of acts that's sufficient to get the theorem to work. So does that answer the question?
Yes, thank you.
Great.
Okay, are there more questions?
Yeah, I'll jump in, John Waymark.
Right.
You know, Franz is there, so correct me if I'm wrong, if misdescribed, because in your paper, you don't cite a manuscript that Franz Dietrich has. I think it's called The Rational Group. Are you familiar with that?
Actually, I'm very embarrassed because I know about this paper and I forgot to cite it. It is cited in the new version of my paper. I just cited it, you know, I fixed the paper to cite that paper because I was aware of it. For some reason, it slipped my mind to put it in. And in fact, Franz, basically, when I sent him a copy of the paper, he very politely and diplomatically mentioned that he had a paper, and you know, so yes, that was a mistake on my part. It is now cited because it is definitely a very relevant paper.
Yeah, so let me just tell for the group because I think they'll find it of interest. And people interested in this kind of topic should read Franz's paper. You know, he's working in Anscombe Almond, but he's building off of Gilboa, Samet, and Schmeidler, as you are, as his point of departure. And he wants the group agent to both have expect utility preference, but use Bayesian updating. And in this Anscombe Almond framework, he shows that if you only apply Pareto when people have the same beliefs, that you can do that if, as in the Harsanyi, you linearly aggregate the tastes, but you need geometric pooling rather than linear pooling, which is what screwed things up for Gilboa, Samet, and Schmeidler. So anyway, it's a nice paper. People should read it who are interested.
I agree. I completely second that. I think it's a fantastic paper. So
We have a new question at the bottom of the chat from Mark.
okay, so Mark asks, can you say more about how you avoid the Mangin impossibility? Okay, so the Mangin impossibility is basically driven by the fact that we're in Philippe's theorem, you're applying the full force of the ex ante Pareto axiom, okay? And the kind of lesson we draw from all of the literature since then is that the full ex ante Pareto axiom is way too strong. I mean, this is sort of a really interesting example of a phenomenon which happens frequently in social choice theory, is that there's an axiom which on paper seems perfectly reasonable, perfectly innocent, seems like a sort of a really minimal condition, but then it turns out to be incredibly strong and gets you into all kinds of trouble, okay? And so Gilboa, Samet, and Schmeidler were able to, in some sense, escape from the Mangin impossibility theorem by weakening the ex ante Pareto axiom. And I have, in fact, weakened the ex ante Pareto axiom. I don't want to say I've weakened it further than they have, because that sort of suggests that my axiom is weaker than their axiom, but I feel like my axiom is weaker than their axiom. And what I have is basically a very weak version of ex ante Pareto, which only applies to agreements which persist in the very long run. And that's how I get away from the Mangin impossibility theorem.
Okay, it was not obvious to me, because I was thinking, suppose people converge to a fixed belief at some point, but they are different. They remain different, but they agree on certain rankings of certain acts, right? So in that setting, your axiom sounds like full ex ante Pareto.
So your intuition is kind of correct. And in fact, that is what happens. What happens is over time, this is not my theorem, this is a very old result. Over time, when a bunch of agents observe a stochastic process and update their beliefs will converge to become closer and closer to one another, okay? So there is a kind of an approximate agreement of beliefs which occurs, but they never agree exactly. But basically my axiom does not require them to agree exactly. But essentially what happens is once their beliefs are close enough to one another, you can apply this kind of weak ex ante Pareto axiom without getting into trouble.
Ah, okay. So that's the key reason, that in fact their beliefs must converge sufficiently.
That's right. And then that's basically this, this condition of concordance in the proof in the theorem is basically what's driving that. So there's an old result of Blackwell and Dubins from, like, I don't know, 1956 or something like that, which basically says exactly this. It says that if you have a bunch of agents whose beliefs are kind of weakly compatible in the sort of sense of concordance, and they observe the same stochastic process and they update with, they Bayes update, then they will converge to have the very similar beliefs in the long run.
Okay. Thanks.
All right. Do we have a final, possibly quick question from anyone? Then we can still deal with that. But if not, then thank you very much once more, Marcus.
Thank you very much.
This concludes the seminar, but Bill will tell us what's going to happen next week.
Yeah, so everyone, next week we have a special version of the seminar. It's our West Coast version. Our speakers will be Francis Su and Matt Jackson. In this California session, the time is shifted so that the California people will actually be awake. It'll take place at 9 o'clock San Francisco time, noon New York time, and 1800, that is 6 p.m. Paris time. So please sign in.
Right, thank you. Yeah, so that's next Thursday. I hope to see many of you there. And that's it for today. Bye-bye, everyone.
Bye-bye.
Bye.